So hello and welcome student to the today's class, and this is course number MA412 linear algebra, and this is lecture number 19. Lecture number 19. Okay. So now so far we have learned about minimal polynomials, and we also proved Kelly-Hamilton theorems that minimal polynomial divides the characteristic polynomial. Okay. Now we would like to also discuss few new ideas. For example, so we know about diagonalization, and that you already learned, and diagonalization. Okay. Now, so this is kind of very nice situation, but every linear operator may not be diagonalizable, right? So the next question is that then what is the next best things? Okay, and this is called something triangularization. Okay. So what does that mean? So that means, so let me define it. So definition. So let same thing. Let V be I'm assuming finite dimensional vector space, and you have a linear operator T on V. Okay, then T is said to be triangulable or triangularizable, both are same. Okay, if there exists a basis of say B of V such that this matrix of T with respect to the basis B is a triangular matrix. So triangular, also triangular matrix, how it look like, right? So basically we will talk about upper triangular matrix here, but similar thing you can do by lower triangular also. So triangular matrix. So we will consider that upper triangular matrix. So by that we mean that this kind of this form. Okay. So so that below diagonal everything is 0, and from diagonal other things can be non-zero. Okay. So this is called upper triangular matrix, right? So if we have this basis, then it's called triangular matrix, triangulable or triangularizable. Okay. So this is not as good as diagonalizable, but this is also nice, because here also you can see that if we have a basis for which this matrix becomes a triangular matrix, then the eigenvalues will be sitting inside the diagonal elements, right? This is a simple observation. Okay. So we can similarly to diagonalizability, you can see the matrix and you can see that what are the eigenvalues, how it look like. Okay. So now to learn this thing, we also need to learn some more definition. So let me start with that. Okay. So let me define something called okay. So probably okay. So maybe I I don't want to define. So there are many technical terms, T conductor, T annulator, many things. maybe let me, okay, so let me define what is T conductor. So this sometimes it's important also. Okay, so definition. So you have something. So let uh, so so T is a linear operator on a vector as V, and say uh, you choose W, which is a and subset of W, or rather I should say T invariant. So W is a T invariant subset of V, and you choose a vector say small v belongs to V, and then you define that the T conductor of V into W is defined by this symbol HT V W. What does that mean? This is collection of all polynomials if x belongs to this polynomial algebra. So this is the field, underlying field, the V over F, right? And such that when you evaluate T, so this will be polynomial T, and the value of this polynomial at V is element of W. Okay. So this is called T conductor of V into W. Okay. So this will collection of all such polynomials is that this will becomes inside this. Okay. Similarly, you can define something called T annihilator. T annihilator means annihilate means zero. So let me write down T annihilator. So one more thing. So whenever we are talking about annihilator, okay. So for when W is that trivial subspace, this is called T annihilator of alpha V. T annihilator of V. Okay, that means collection of all such polynomial such that f of T of V equal to 0. Okay, it annihilates that vector. Okay, now it is very easy to check that this properties. So this collection has nice properties. So in fact, this is an ideal actually. Ideal of this polynomial algebra. Okay, so why it is not? Okay, so before that, we note that whenever W is T invariant, then whatever polynomial you choose, which is polynomial in T, W will be invariant under the same polynomial. Okay, so maybe let me tell you that this. So in terms of a theorem or proposition, okay, so then I will come to the proof of this, but let me just write down that thing. So let W be a T invariant subspace of a vector space V over a field F. Then W is invariant under any polynomial, invariant under any polynomial in T. Okay, and that is obvious proof. Now, so you choose any polynomial, say fx equal to of the form, say summation ci x power I, say I equal to say 0 to k, and if you substitute the value f of t, then it will be summation. Okay, uh, so the first term will be c0 identity plus c1 t and so on, right? Ck t power k, right? Now when we evaluate some vector of w, then what will be? This will be c0 w plus c1 t w and so on, ck t power k and w, right? But note that this is element of again w, because tw t invariant, so tw is element of w, and hence so is t power kw, right? And then if you add all those elements, it will be again an element of w, because w is subspace. So this shows that and w that w is f of t invariant. Okay. Okay, now so if you know these things, then what happens? Then you can talk about this whatever I just said. You choose any polynomials here, and you say the sum of two polynomials is again inside here. Okay, because if for first, okay, so to prove one, note that if say f1 and f2 belongs to say st of vw, then what happens? Then any combination of those things, for any combination, some constant c f1 plus f2, again element of this. Okay, and not only that, if you choose any another polynomial, say f dash or belongs to say polynomial algebra, and f1 belongs to this t conductor of v into w, then the product f dash f1 is again element of this. This is also obvious fact. Okay, so because so if you write down this, this is f dash of f1 of t, and this will be nothing but polynomial f dash t into f1 of t. Okay, and this has to be element of this, because when you substitute the value v here, so f1 t will be element of w. Okay, and f dash t is also because w t invariant, f dash t send that element to w again, right? So this will be an element of w. So this shows that what I claim is an ideal of this. So we can talk about the generator, right? So this is very important. So this is VW, so that generated by single element, because this is a principal ideal domain. Any polynomial algebra or field is a principal ideal domain, and hence this will be generated by some gx. Okay, and what is the importance of this gx? Sometimes this gx is also called t conductor by same name. Okay, but important thing is that this gx always divides and the minimal polynomial, polynomial for t. Why? Because if px is the minimal polynomial for t, then you know that pt equal to 0, and hence pt of that vector v equal to 0 vector, right? This is identically 0 means 0 vector, so this is an element of w. So what does that mean? That means px is an element of st vw, right? Because px is such a polynomial, so this pt of v element of w. So px is element of this t conductor v into w, and this is a generator, gx is a generator. So that's what divides this thing, right? This is the differential algorithm or equivalent algorithm. Okay, so this means gx divides px. So what does that mean? That means gx is the so how do you say that? So you can say that gx is the kind of the least degree monic polynomial such that gt of v is element of w, and whatever other polynomial you choose into the conductor of v into w, there will be multiple of gx. Okay, this is important observation. Now with this observation we'll try to prove nice theorems. So first we will start with the following lemma, and so this lemma tells what? So say I am assuming that v is finite dimensional. So let so dimension of v is vector space, so dimension is finite dimensional. Okay, and over some field. Okay, so for f. Okay, and then t belongs to the LV, the linear operator on v, such that the minimal polynomial, polynomial for t is of this form. So this is kind of a product of linear factors. So that what does that mean? That means x minus c1 power something. So maybe let me say d1 x minus ck power dk, where these are the c1, c2, ck set the eigenvalues, right? Because you know that minimal polynomial and characteristic polynomial are the same roots, so they are the eigenvalues, where c1, c2, ck's are eigenvalues of t. Okay, so you have eigenvalues of t, and then you write down these things. So these ci's are element of f. Okay, so if this is the case, then what happened? Then there are some nice thing happened. So so now let w be a proper subspace of v. I mean, you choose any proper subspace of v such that w is t invariant. W is t invariant. Okay, so v itself say t invariant subspace, but you need something which is proper subspace of v, right? Then what happened? Then with this condition, then there exists. So with this all this condition, you can say something. What is there exists some vector v belongs to v minus w. That means element of v, but not element of w, such that so you can choose this. Okay, so obviously you can choose a vector which is in v, not in w, because w is a power subspace. But this vector has a very nice property. What is the property? Such that when you apply t minus some ci, so I should not say that. Maybe I should say c of I of v. This is the element of w. Okay, for some c equal to ci's. So this is c is a characteristic eigenvalue. Eigenvalue means this will be one of those c1, c2, ck's. Okay, for some, I don't know, it may be c1 or c2 or ck. One of those things is going to happen. This. Okay. Now, with the help of, so what does that mean? That means I am saying that the T conductor of V is actually linear. So x minus C is actually belongs to STVW. This is the theorem telling. Okay, so you can find out an V which is not inside W, whose T conductor is linear. So this is element of this means what? That means so the generator will be of this form, right? They are linear. Okay. Now, okay. So proof. How to prove this? Proof. So we start with that. So let your ST. So maybe I can start with any vector, say. Yes. So let me. Here I wrote V, right? So let me write down another name. Maybe something, say. So let some vector which you say V dash, which is the element of V but not inside W. And then let you choose this T conductor of V dash into W, and suppose this is generated by as a polynomial Gx. Okay. Then obviously this Gx will also divide the minimal polynomial of T that I already showed you, right? So Gx will divide the minimal polynomial. So this is the minimal. Sorry. This is the minimal polynomial for T. Minimal polynomial for T. Okay. Then what happened? Then Gx will be. So I already assume the minimal polynomial is product of linear factor. So what does that mean? That means this will be also sum of those things, right? Something say x minus c1 power, something say e1. I wrote d, so I choose e. Similarly, x minus ck power ek. And those some of the EIs may not be even non-zero, something maybe zero also, but at least one has to be non-zero, right? Because this Gx is that Gx is a T conductor, right? So Gx this minimal polynomial, and I choose this V dash is outside W, right? So Gx cannot be constant. Then if V dash is inside, if G is constant, then that means constant can be as an element of W, but that is a contradiction. So G has to be some non-trivial, non-constant polynomial. Okay. So what does that mean? That means G if you choose G of this form, so at least one of the Ci is non-zero. So let you choose maybe E of J is something is greater than 1. Okay. And then you can write down this Gx will be that Ex minus Ej is Cj or Ej is power of x minus Cj. So at least one of the factor x minus Cj will be there with some other polynomial. Okay, with some other, right? It can be 1 also. This hx can be 1 also, constant also, right? But doesn't matter. Whatever the polynomial, Gx will be of the form x minus Cj times some another polynomial that can constant polynomial also. Now, what is this vector? Now consider. Now I am claiming that the vector v is like this. This h of t when you evaluate v dash. This is the vector which I am looking for, whose when you apply t minus c, that will become t minus cj, that will be inside w. Why? Because now first of all this polynomial is outside w. Why? Because if it is inside w, so this is, so consider v equal to ht of v, and then note that this v, which is ht of v dash, is not inside w, as otherwise what happened? otherwise h of x will be element of the T conductor, right, of V dash, and this implies this is, if this is an element, then what happens? Then this implies gx will be divides hx, by which is a contradiction because hx is a factor of gx, so this is a contradiction, which is a contradiction. Okay, it's not possible, and hence this hx cannot be element of this, so thus this v, which is h of t of v dash, it's not inside w, right? But when we apply t minus cj I of on v, then this will be nothing but t minus cj I of ht of b dash, right? But what is this? This is nothing but, see, this is nothing but gt, right? Gt of this. So this is nothing but gt of v dash, right? But by definition, gt is that inside the this generator or conductor of v dash. So this has to be element of w. So this is element of w. So see, though b is not element of w, when we apply t minus cj of b, that is element of w, and this is the lemma. So that, okay. Now why this lemma is important? This lemma tells you actually that whenever you choose element, so if you choose a proper subspace, which is a t invariant subspace, then you can find out always an element outside that invariant subspace whose the conductor is actually linear. It's not constant, it's a linear things, and this is going to help us to prove our next theorem, and that theorem tells us that it's very important theorems on triangulable criteria. So this says that okay, so let me write down. So let V be a finite dimensional vector space over a field F, and you choose T is a linear operator on V, and then you can say that then T is triangulable if and only if the minimal polynomial of T, minimal polynomial of T is product of linear factors. Product of linear means degree 1 polynomial, okay, but I am not saying this thing, the product can repeat also, so product of linear factors. Okay, this is if and only condition. So if you check something is triangulable or not, you check how the minimal polynomial look like. If it is a product of linear factors, so if there is no quadratic or higher order terms, then it must be triangulable. Okay, and the one part is obvious. Okay, so which one is obvious part? So let me do the proof. So one part is obvious. If T is triangulable, then what happen? Okay, so if T is triangulable, then what happen? Then there exists a basis, by definition, say V may be of this form, V1, V2, Vn of the vector space V, such that such that the matrix representation of T with respect to this basis B will be triangular matrix, right? Something like that. Say something like that. Whatever, maybe you can write down C1, C2. I mean C1, C1, C1. Sometimes C1, and then C2, C2, C2. I am not saying this thing, right? And then CK, CK, CK. And this part is 0, and upper end can be anything, any non-zero element or 0, doesn't matter. But below diagonal everything is 0. Now what is the advantage here? Advantage is that triangular matrix, when you know the triangular matrix, you can easily find out the characteristic polynomials, because characteristic polynomial will be nothing but so thus, so if this is the triangular form, so the characteristic polynomial carry polynomial of T, that will be what? That will be of the form x minus c1 power some m1 and x minus ck power mk. And this m1 is what? M1 is representation of c1 inside this diagonal. Similarly, m2 is representation of c2, and so that mk is representation of ck. How many times repeating, right? These are actually algebraic multiplicities. Okay, so and you already know that minimal polynomial divides characteristic polynomial. So thus, by Kelly-Hamilton theorem, Kelly-Hamilton theorem, the minimal polynomial, will be what? So that will be of the form is some divisor, right? So it will be something x minus c1 power some d1 and x minus ck power dk. So these di's are actually less than equal to mi's. Okay, and this is at least 1, because all the roots of characteristic polynomial should be also roots of minimal polynomial. That also we learn. Okay. So this is the proof, one part. So next part is important, for which we need this property which T conductor that we use, right? Conversely, the converse part is what? Conversely, we assume that minimal polynomial is of this form, right? Conversely, let and the minimal polynomial of T is say Px will be of this form, say x minus c1 power d1, x minus c2 power d2, and so on, right? X minus ck power dk. Now we'll show that the then T is triangulable, means there will be a basis with respect to which the matrix of T will be a triangular upper triangular matrix. Okay, then what we will do? So we'll try to find out the basis. So we'll start with 0 space. So let my W0 is that 0 space. Okay, and obviously when you have a 0 space which is T invariant, so which is T invariant, right? Because null space is T invariant. This is the trivial space, right? So for this T invariant space, we will apply the previous lemma. There exists a basis vector. There is a vector for which what happened? So vectors for which something happened, right? So what is the thing? So then there exists some vectors. So v1 belongs to V, which is not element of W0, such that what happens? Such that whenever you choose this vector, then such that T minus Cj, so Cj is one of the eigenvalues of this linear operator T, right? Some Cj. So I don't know. So maybe I can write down C1 only. Okay. So C1 of I of this V1. So this is the element of W0, which is 0. So what does that mean? That means actually V1 is a eigenvectors for T with respect to eigenvalue this. Okay, that is possible. So that is what, that is, you can write down T V1 equal to C1 V1. Okay. Now once you get this vector V1, so now you find out the subspace spanned by V1, which is W1, W in the subspace spanned by V1. Okay. And you see that because V is a V1 is a eigenvectors for T, W1 is T invariant. So this implies W1. Okay, sorry. So this implies W1 is T invariant. Why? Because T V1 equal to C1 V1, right? So W1 T invariant, right? And when W1 T invariant, then you can apply the second that lemma again. So for W1, so there exists. So you can find out. Okay, so that there exists. So thus there exists some V2. So what is your V2? So V2 is that okay. V2 is the vector that exists belongs to V2, so that is inside V but not inside W1. W1 is spanned by V1, remember, such that T minus something, say C2 of I of V2, this is the element of W1, so this is belongs to W1. What does that mean? That means, so this quantity is actually multiple of V1, right? So that means T minus C1 1 of V2 will be some constant. I don't care whatever the constant. Okay, maybe say C12. Okay, C12 of V1, right? So what does that mean? That means T V2 is nothing but C2. This is C2 V2 plus C12 V1. Otherwise, you can write down the C12 V1, C2 V2, right? And so on. So, and then you continue this process. Now, what is the next thing? The next thing, you choose W2, which is the vector space spanned by V1 and V2. Okay. And you choose V3, which is outside. So you choose V3, which is outside V minus W2, right? Now you can do same process, and because V is finite vector space, this process will stop somewhere, right? So now you should check that this V1 V2 they are actually linearly independent. The way I am choosing, right? So this finiteness of V will tells you that this process will stop, and then you can find out some vector, say V1 V2 Vk up to Vn whatever, and what happens such that repeat this process to get these vectors V1, V2 and Vn. And now you look that the way I choose V1, V2 are linearly independent, right? The way I am choosing, because V2 is not inside V1, so V2 cannot be linearly dependent on V1, right? Similarly, V3 also. So we get this such that what happens such that T of this Vj, that will be nothing but, you start with C1j. Okay, so let me write down this, maybe C22. Okay, this C22, C11, then it will be a nice thing, C11. Okay, TB1 equal to C11 V1. So this C11, C22, C33, these are the diagonal elements, and those are the actually your eigen values. Okay, so you can find out these Cij's and V1 plus C2j V2 and so on, Cjj
and then Vj, and this is true for all j in between 1 to n, right? So what does that mean? That means when you write down the matrix representation of t with respect to this vector, so this is I am writing that in B, because B is linearly independent and has n many elements which is dimension of V, so this will form the basis of V, right? Now with respect to this basis, what will be the matrix representation of T? This is exactly what we want. So this will be um, exactly this form, right? This is exactly C11, then C22, and then CKK, which are the diagonals, and here you will have C12 and so on, right? And this will be 0. Because why this part is 0? Because when you compute V1, this will be C11 V1 and S star 0, right? So the first column will be C11 and everything is 0, right? Similarly, in second column, you see the same column, there are two vectors, V1 and V2, and everything is 0, all the coefficients are 0. So second column you will have C1 to C22 and everything is 0 here. So that the below diagonal everything is 0. So this will be triangular matrix, and hence proved. Hence T is triangulable, right? So this is the proof actually. This is the proof of the theorem that if the minimal polynomial is product of linear factors, then it is also triangulable. Okay, this is one condition. Now, can you relate this thing to that something called our diagonalization, which we have already discussed? And the answer is yes. And this is very important theorem that tells you that I mean with the same condition, whatever condition I'm assuming, V is find dimensional everything. T is diagonalizable if and only if the minimal polynomial for T is product of, see last time I wrote this is linear factor, right? Product of linear factor, but here I am assuming one more term, product of distinct linear factor. What does that mean? That means each of the linear terms will come once only. Okay, distinct linear factors. Okay, then T is diagonalizable. Okay, so this is a different condition. And now proof. So how do you prove this thing? Okay, so proof. So one part is what? So let T be a diagonalizable linear operator okay, and then let that C1, C2 and Ck's are distinct eigenvalues of T. Okay, and one more. So I'm also assuming, so this is diagonal. So what does that mean? That means you can find out then there exists a basis of B, say V1, V2, Vn consisting eigenvectors of T. Okay, so this is the definition. I'm using one of the equivalent definition of diagonalization. Okay, so you can find out this basis such that this eigenvectors, right? Now then what does that mean? That means so you start with the operator. Now consider this polynomial, say px, which is equal to x minus c1
x minus ck. So this sorry, this is product of this. Okay. Now if we take these polynomials, so this is a linear, there is no repetition. Then what does pt do? So pt will be the polynomial t minus c1i and t minus cky, right? Product of these. Okay. Now because we have a basis v1, v2, vn, which is a basis of eigenvectors, so you can know what happened to say t of say vi. What is the value of this? So vi is a eigenvectors corresponding to t, right? So that means vi will be eigenvector for one of the c1 to ck, right? So you can write down t c1 I c vi, right? Now this vi, which is a basis vector, is also eigenvector for t. So what does that mean? That means this is eigenvector for some ci, right? So there exists ci eigenvalues of t such that this t minus ci of vi, that will be 0, right? This is eigenvalue, eigenvector, right? But so this factor t minus ci is one of the factor, right? So that means this portion will be 0, identically 0. This is 0, right? And this is true for every vi. This is true for everywhere, right? For every vi, it will be eigenvector for some eigenvalue, right? So what does that mean? That means p sends every vi to 0 vector, right? So thus, what does that mean? That means p sends every vector to 0 vector, right? Because these vi's forms a basis, and any vector is a linear combination of basis vectors. So if some polynomial sends every vector to 0 vector, every basis vector 0 vector, so that will send all the vector to 0 vector, right? So this tells you that px is an annihilating polynomial, polynomial for t. But this is also we know that if it is minimal polynomial, should contains all the roots, right? So it has to be minimal polynomial, right? Because minimal polynomial is the least degree such form, right? So as minimal polynomial share the same roots, with characteristic polynomial. So what happens? Then P has to be this. Then P is the linear polynomial, right? Because linear polynomial is the least degree monic polynomial for which that linear operator vanishes, right? That annihilates t, right? So this is one part, obvious. So next part tells you that if conversely, suppose the minimal polynomial is of this form, product of this linear factor, then it's diagonalizable. Now how do we prove? So conversely, let the minimal polynomial of t is of the form px equal to x minus c1 up to x minus ck, where the ci's are all distinct. Ci's are distinct eigenvalues of t. Okay. So if this is the case, then what you can choose? You can choose the eigenspaces, say say let ECI be the eigen spaces of T corresponding to Ci corresponding to Ci's. Okay, so if these are eigenspaces corresponding to Ci's, then what happened? Then you take direct sum. So may say let W be the direct sum of this, direct sum of ECI's. Okay, 1 to k. Now, if this direct sum is W V, then we are done. Then this is diagonalized, right? That we already proved. If direct sum of eigenspaces is the full space, then V is diagonalizable, right? But suppose not. Suppose I don't know. So let me prove that this is not diagonal. I have to prove this diagonal, right? So I am assuming that this is not diagonal, and then find out the contradiction. So suppose this is not equal to V, then what happens? Suppose. So this is I am supposing. So if this is not equal to V, then what happens? So now anyway, you see that these eigenspaces are always T invariant, right? So W is T invariant. And if W is not equal to V, then the lemma we used before, you can find out you can find out the vectors which is not inside W. Then there exists something, say a vector say alpha belongs to V not inside W, such that what happened? Such that this that T minus, okay, so I am choosing C1, so you can choose anything, so it doesn't matter. So there exists some eigenvalue, so without loss of generality, this is eigenvalue C1, so T minus C1 of I of alpha. So this is kind of say vector beta, say, so this is the element of W. So you can choose something outside W and send it to inside W under the action of T minus C1 of I, right? And so there is no speciality of C1. This can be true for any C1, CIC, C1, C2, Cn. Okay, just I choose this thing, right? Now this vector beta is inside W means what? That means beta can be written as element of say beta 1 plus beta 2 direct sum of beta k, where this beta is an element of ECI's. What does that mean? That means these are all eigenvectors actually. So beta 1, beta 2, beta 3 eigenvectors, and then sum of eigenvectors. Okay. And what does that mean? That means that when you substitute T beta I, and then it will be nothing but Ci beta I, and this is true for I equal to 1, 2 up to k. There are k many eigenvalues. Okay. Okay, so what does that mean? So if this is the case, then when you substitute, this is for any polynomial. So thus for any polynomial, so h of t, when you substitute beta, then this will be sum of that individuals beta is C1, beta 1, and HC case, beta case. This is the simple observation that if T is eigenvalue, if C is eigenvalue for operator T, and then if you choose a polynomial F, then F of C will be eigenvalues for the polynomial F of T, right? The simple observation. And this is true for any polynomial H belongs to polynomial algebra, I will have this thing, right? So now note that you can write down, say, my polynomial Px equal to Cx minus C1 into another polynomial Qx, right? So why I am choosing C1? So there is no speciality. This can be any Cj's, right? I choose because of simplicity, and my Qx will be something x minus C2 up to x minus Ck's, right? Now note that when you replace Qx minus Q of C1, then what happens? Then it will be actually the the constant term C1, C2, C2 will get cancelled, and it will be actually nothing but x minus C1 times some polynomial. Some polynomial. For example, if this product of two factors or so one factor, whatever. So this is simple observation. The homework can do it. Okay, you can do it. You just start with say two factor, check what is happening. Okay, so this will be this because so the highest leading term here will be x to the power k minus 1, right? Similarly, when you multiply, you subtract x minus c1, you will have c1 power k1. So x minus x to the power k minus 1 minus c1 power k minus 1. So x minus c1 will be factored. So that will be common. Okay. Now if this is the common factor, then if you evaluate your t on this, then you find out that qt on alpha minus qc1 of alpha, this will be nothing but your h of t into t minus c1 of I of alpha. Okay, because of this identity star. If you replace x equal to t, then you'll have this. Okay, but what is the advantage here? So advantage is that now note that this is beta, right? So this one is beta, which is already I assume. Yes, this beta. So this is nothing but ht of beta. Okay, but beta is inside w, and w is t invariant. So ht of beta is also inside w. W is t invariant, right? So is invariant under any polynomial. So what does that mean? That means the right hand side is element of w. Similarly, this polynomial, you see that qt of alpha is what? This is nothing but so this is also element of w. Why this element of w? Because if you multiply qt of alpha by okay, so the first one, right? So this belongs to w as t minus c1 I of qt of alpha. This is nothing but c minus c1 alpha is nothing but pt of alpha, but this is 0, right? Because p is the minimal polynomials. So what does that mean? That means these elements of ct of alpha is okay. So note that this one t minus c1 of I is so this is 0 means what? That means this qt of alpha is an eigenvectors for c1, right? That's why when you apply on t minus c1, it will be 0, right? And because this eigenvector, it has to be element of w, because w is collection of all the eigenvectors, right? So qt of alpha is element of w. So what does that mean? That means this equation say 2, the right hand side element of w, this is right element of w, so only this part left, linearity tells you that this has to be element of w. So thus qc1 of alpha is element of w. Okay, but note that alpha, the way I choose alpha is outside w, right? So see, alpha is outside w, but qc1 alpha is inside w. What does that mean? That means there is only one option. This must be 0, because 0 vector is element of w. There is no other multiple of a vector inside w other than 0 multiple, right? So this implies q of c1 has to be 0. But if q of c1 is 0, but q of c1 is what? Q of c1 is nothing but c1 minus c2 and dot c1 minus ck, right? Because c1 qx equal to of this form, x minus c2 to x minus ck. So when you replace x by c1, it will be c1 minus c2, c1 minus c3, and c1 minus ck. And if you product of this, now this is impossible because I choose that c1, c2, ck all are distinct, right? So this cannot be possible. So qc1 of 0 is, which is a contradiction.
which is a contradiction. This is C1 minus C2, C1 minus C3, and C1 minus CK. As all the CIs are distinct, Okay. Now, why we get the contradiction? We get the contradiction because we assume that W, the subspace span sum of all the eigenvectors, is not the full subspace, right? This is the contradiction. So what does that mean? That means W has to be equal to V. So thus W, which is a direct sum of eigenspaces I equal to 1 to k, it has to be equal to full V, and hence V. So what does that mean? That means T is thus. So this tells you that T is diagonalizable. That I already proved, right? T is diagonalizable. Okay. This proof is a very critical proof, but I assume that you understood it. Otherwise, we will discuss on live class. Okay. I will stop here.